And the real allure of having to deal with local and global responses, or how does the system respond locally, and then how should the whole system respond globally. So in the event that you do have a failure, you can continue to live, or your system can survive, but there is a need to then balance the life of that system with the usefulness of the system, whether or not it meets mission or user needs. The other problem that we run into with these large distributed systems is that oftentimes they divide up the development or um, the responsibility of these subsystems to different organizations, different developers. And that's great, but it ends up giving you varying life cycles and development that you have to deal with, different products that you have to work with, etc. So then on our side, one of the major challenges is providing and maintaining assurance of these various subsystems as they change throughout the entire life cycle. And in some cases, the system will continue to change even after launch. So how do we continue to provide assurance on that end? Now, one of the more recent challenges that we start to face is that a lot of these systems are becoming very data intensive. So what that means, in a sense, is that a lot of the requirements that would have been allocated to software are now being deferred. Not only requirements, but behavior of the system is being deferred to these data structures that either aren't defined early, plan to define later, or will be defined at some future point after the launch of the mission. So of course, this poses a challenge because we don't have all of the system behavior defined by requirements, and even don't have the system behavior defined prior to launch, and it's always subject to change. But this is just a natural progression of things, because you could look back a couple years and see a lot of requirements allocated to software that would have been allocated to hardware. So just some of the challenges that keep coming up as we try to provide assurance. And of course, the bottom there, the challenge is we can't provide 100% verification. No one can do that. You can't test everything. You can't provide 100% assurance, and you can't guarantee 100% success. So then we're left with how much assurance is enough, and how do we do that in a cost-effective manner. And what I'm going to focus on is for software assurance. So looking a little deeper into the fault management assurance goals, if we look at fault management, as I said before, the allure of the network or distributed system is that it's able to tolerate failure. That's great as long as you have identified all the failures in your system. So you have to have a complete set of failures so that you can then determine what the impacts are of each of those failures, not only at each node, but the adjacent node and then throughout the entire system. Only then can you figure out what controls you need or mitigations need to be in place, such as reliability or redundancy, those type of design considerations. And then on down the line, you can come up with software requirements. But you also have to balance, of course, the needs of the user and the mission with preserving the life, as I stated before. And only then can you hope to have a complete list of fault management requirements at the software level. Verification poses other problems. The hope is that if you do have every fault management behavior for software dictated by a requirement, then there's numerous processes at IV&V to do verification of each individual requirement. The problem is that even if you do verification and traceability to all the required behaviors that are defined, you still have a combination of behaviors that emerge based on the other requirements in your system. So then how do we ensure that we don't have conflicts with the fault management system and the end users who are using the system and the other subsystems that are trying to accomplish their own goals? So then that, of course, is our goal, is finding conflicts within these controls and other systems. So here at IV&V, our primary goal is to answer the three questions: Q1, Q2, Q3. Q1 being, does the system do what it's supposed to do? Q2 being, does it not do what it's not supposed to do? And those are decidedly very easy to address rather than Q3, which is, does the system behave properly under adverse conditions? Q1 and Q2 are almost always dictated by requirements or the inverse of requirements, whereas Q3 would be anything that isn't dictated by requirements. So those are your unknowns. And we have lots of methods that handle how to do verification of requirements once they're defined. But for Q3, does the system behave properly under adverse conditions? The only way we can really determine this or provide an effective set of assurance is to have a complete list of all the credible failure conditions or adverse conditions. And there's two major ways in which these are usually derived. One being a brute force or bottoms-up method, or a testing approach method, where you throw every single scenario at your system, having a very good high fidelity system, go through all the possible states in theory, every combination of states, and then you see what happens. If it fails, well, you've got a problem and you can fix that. If it doesn't fail, then you're okay. The problem with this approach, of course, is that you can't do 100% verification, can't do 100% testing. So in theory, it sounds great, but in practice, it's impossible. So you end up doing some sort of tricks in order to do as much testing as possible. The most common method would be Monte Carlo, for example, where you're testing some random states and hoping to get some assurance based on the amount of coverage you can provide. The only problem with this is that, of course, it's very resource intensive. It's very costly to do this. And you have to wait until the system is well defined before you can do the testing. And as we stated before, you have a lot of behaviors that are being defined ad hoc or deferred late in the life cycle. So if you start doing your testing too late, then you won't finish. And even if you do your testing early, can you still have any faith in what you found before as being accurate because your system's now different? The second approach, which is more popular, is top-down. And the most common method for top-down approach is fault tree analysis, where you get some very smart individuals who decide what events they don't want to happen, and then they work backwards to determine what chain of events can happen to get you to that state, and then you try to prevent those from happening. And this is usually what is performed on majority of the missions, obviously because it is less resource intensive, it's less costly. The only problem is that this method will tend to provide fewer scenarios for testing and assurance than even the nominal or Q1 set of scenarios. And we all know that there's a lot more off-nominal scenarios than there are nominal scenarios in the system. So having fewer adverse scenarios to test through is not going to provide you the assurance or sufficient assurance usually. So then what is the third proposal there is what this method's really about. It's something intermediate, using a limited bottoms-up approach and the top-down approach. You could say it's like a middle-up to determine potential conflicts and then work backwards, similar to fault tree analysis, to determine whether or not scenarios are credible. And hopefully this approach will be more cost-effective and efficient than bottoms-up. Obviously, it's going to be a little more costly than top-down, but it will provide better assurance in the end. So then here in this diagram, I tried to create a really crude two-dimensional representation of the state space to try and illuminate what we're talking about here. You can see the orange line going straight up through is the nominal path. So if you can think of these, every point in this two-dimensional space being a combination of states, and that orange path is the nominal path. It just happens to go in a straight line, which is good for us. It's easier to see. The blue dots there represent major points in the mission or phases of the mission, where we'd want to get to those points and then revert back to them. You can see the red lines going through between the blue dots are what the proposed fault management scenarios would be, where a failure would occur and that you would want to then get back to a known safe configuration. That large circle or oval in the middle there is a representation of a random state coverage through Monte Carlo or some other means, where you have a completely random and completely distributed set of test cases or states that you would hit. And you can see that in this case, it might catch two of the conflicts, which are depicted by the tan circles. So what the method is trying to propose is that we assume that a lot of the failures are going to be, or a lot of conflicts or problems that we would encounter in the mission or the unknown unknowns are going to be grouped together and based on a combination of states. So if the conflicts are located in a combination of states, if we abstract the whole system, we can identify these green bars or a collection of states where we're more likely to find conflicts, and those would be what we're trying to identify. And then we can test those through static and dynamic means in order to determine if there are any failure conditions or violation of the mission. So then the approach then is top-down to develop a conflict set of rules for the conflicts, or how can we violate user or mission needs, and determine the known failure modes to medium fidelity model of the system. In this case, we're using the term event network, with emphasis on the software perspective for two reasons. One, it reduces the size of the state space of our model system, and two, that's the focus of IV&V assurance, is on the software and not the entire system. Although, of course, you could expand this to be more encompassing. Then applying automated and scripting principles to establish scenario coverage of the system model, and then through rules checking can determine whether or not a conflict is possible, and then through analysis determine whether or not those potential or suspected conflicts actually exist, and then through more detailed manual analysis or even high fidelity simulations or tests confirm or deny the conflicts. So what this all really hinges upon then is having a relational database in order to capture the relationships between the system components and the software, and a traceability matrix within that relational database, along with a system model or event network, conflict rules, and in our case, well, we have the added benefit of having a test bed in order to actually execute and verify that we have found problems. So then this slide here just shows the approach process. The actual process takes about 3 phases, or we broke it into 3 phases. And the first step, of course, is traceability and validation of the fault management requirements themselves. So in some cases, we may or may not go back to the failure modes and effect analysis, the FMEA, or the fault tree analysis in order to validate the requirements. But in this method, it's essential that you do that so that you have an understanding of how each of the components in the system interact with one another, and what sort of impacts failure of any of those items is going to have on the software and the whole system. So this then helps us to validate the requirements that are in fault management, which towards the end of there, you would see that the requirements, design, source, stored sequences, and or stored commands and test artifacts would all get mapped into a lifecycle traceability matrix beyond just the requirements and those artifacts, is so it can generate a software fault dependency report, or a mapping of how these requirements are related to the system components, which is important in the next step, which is generating a system model or an event network. So in this case, you would take design documentation and system specs and other items to compile a list of all the components, modes, and states within the system, and sort of compile a state database or a state table, and combine that along with the commands and telemetry that this system is going to respond to. These would be the messages in your network. And those, of course, would be derived from this project's together, you can determine how the commands and states relate to one another. For instance, command to turn the heater on would then map to an event where the heater is on, which would then relate to telemetry items indicating that the heater temperature was increasing, so on and so forth. We take the fault management data that we had before, including the requirements that are indirectly mapped, and map these to the state and command events that we have, and then we take the stored commands, which is basically just a collection of all the commands that we've already defined, but there is a sequence associated with the initial event occurring, resulting in two state changes. State 1 is a trigger for the first fault, fault 1, which results in a response of stored commands 1. At the same time, we see that state 1 and state 2 are both conditions for fault 2 to be declared, which results in the second stored command sequence, which then results in the first stored command sequence. So here we're highlighting the potential for a violation of some rules. You could have two sequences firing at the same time or calling the same sequence at the same time, two faults occurring concurrently based on one single failure. So if you're single fault tolerant, that would not be appropriate. Then by doing all this, of course, what we're ending up with at the bottom is dependency mappings and reports that indicate what hardware is pertinent to fault management, as well as what stored sequences are pertinent to fault management. That way, if any of these items change later on, we'll be able to see exactly what events and what requirements are directly impacted as we move through. And the other big item here is that this is intended to be iterated as products get developed. Okay, the third approach, or third process in this, is actually the analysis of what we've compiled in our event network. And by taking the event network and starting with one or more events or combination of events, we derive a set of scenarios. And these scenarios then can be analyzed for conflicts. The conflicts then would have to be compiled from mission and user needs, concept documentation, or if the project has a database of limitations and constraints, or other such information from design specs that indicate limitations of the hardware, those could all be incorporated so that we can see whether or not a potential conflict results. In this example here, I have a sample rule where A side is active and B side is active. So we never want to have both sides active at the same time. So if you were to run through the scenarios and see that A is active followed by B active, it would have to be analyzed to determine what's going on. An important aspect of this event network is that time is not modeled. It's quasi-dynamic because it does model the sequence of events, but it doesn't model the time between each event occurring. So that's why it only illuminates potential conflicts. Also, in this sample problem that we have where both A and B are active, there may be some problem in our model where the sequence then gets updated so that every time A is activated, B is inactivated, and vice versa. In that case, there's no way to violate this rule, and we wouldn't have to worry about that one anymore. But once we have these potential conflicts, they can be analyzed through static means, through just desktop calculations, and do some timing analysis at the desktop to see whether or not they are credible conflicts or events. In some cases, though, there is a combination of states that simply cannot happen due to environmental constraints, etc. And then those would have to be backpropagated into the system model or the event network so that those things don't keep popping up over and over again. in this case, what we wanted to do was take these potential conflicts and create test scenarios that we could then run on our test bed. So again, we're fortunate that we have a high fidelity test bed that we can run these scenarios, and in some cases it's not possible to prove or disprove that these conflicts will occur without including timing. And so by way of this method, we would generate scenarios and that would be either exercised on our test bed or the project's test bed. And then at this point also, once we have all this data in hand, we can then do full change impact analysis for anything that's changed in any of these scenarios that we create and execute our assurance that, again, we can maintain and provide. So here this is just a real simple example of the overall approach. In this case, we have a very simple system. We have a light bulb, a switch, and a user. The user can be thought of as our software system. And from the FMEA, I have the components and states listed that indicate for the light, it has 3 possible modes: on, off, or failed off. And the switch has 4 modes: open, closed, failed open, or failed closed. We know that our software has 2 possible actions it can perform. It can toggle the switch and it can change the bulb. The software's purpose, or the user's purpose here, is to keep the light on at all times. So that's their main goal. The fault tree analysis at the top has indicated what sort of events could happen to cause the light to not be on. And one of those is that the light is off, and the other is that the light's failed off. And we see that the light could be off because the switch is open, or the switch is failed open, or that the power supply is failed. Now, the software has no direct way, or the user software does no direct way of seeing whether or not the power supply is failed. It doesn't have insight into this. So if we model our system based on what the software could do, we see that the power supply failed in the event network over there. That's the top event. The light turns off, and we see that this results in a light off fault. So the user is aware that the light is off. So what does the user do? It toggles the switch. And toggling the switch means turning the switch open and closed to those states. Every time the user would close the switch, as well as the light being off, we get a little bit of recursion here where if the light's off and the switch is closed, the user assumes it's a dead bulb. So they're going to change go through more than 1 bulb a day at most. So in this case, we have a conflict in our system where the software doesn't know enough, the system doesn't know enough in order to be effective, and breaks the mission rules. So if you think about this, you want to add more complexity to this, you can start adding more users. Let's have 1 user only control the switch, 1 user can only change a light bulb, and another user can talk to the power company to find out whether or not the power supply is working. And of course, if you start adding that complexity in there, I'm sure you can think of a lot of different scenarios or things that can go wrong when you have 3 different people operating 3 different devices, and there could be disastrous consequences when they're not communicating properly with one another. So then, so far to date, we have used this method in the first phase, and we've started to go on to the second phase, and or we've done 1 iteration of the second phase, and we're working on a third phase. And the first phase was the database or the traceability or integrity analysis of the fault management requirements and the FMEA and FTA analysis that the project had done. So going through all of that assessment, we found several high severity issues where they had a missing requirement to do a fault. It was clearly stated in the FMEA analysis, and there was even a fault identified in the fault tree, but there were no software requirements to actually check for and raise the fault. In another case, they had a fault identified in the requirements. They were checking for the condition, they were raising the fault flag, but they had no requirements to support collection of the data in order to actually monitor for the fault. So they wouldn't have any, it was either going to be stale data or garbage data that they'd be actually checking for fault condition. In addition to that, through the use of using the database structure, we could see that there were a lot of lower severity issues where the integrity of the data was not complete. There were improperly identified and mapped items that would impact the developer's ability to provide assurance that their fault management system was complete and correct. So right now, there's a lot of activity going on right now to continue doing life cycle traces of the entire system. And there was a lot of activity previously because this project's gone on for several years. There's a mixture of past and present ways of doing traceability, spreadsheets, activity diagrams, databases, etc. So that's all going on, and we completed the first iteration of the event modeling for one of the subsystems, one of the larger subsystems with most of the fault management actually active in it. And the benefit here was that it was later in the life cycle where most of the software behaviors are defined, and we had to do some work to create some custom modeling and visualization tools so that we could see the event network as we were developing it, and to analyze it with some parsing scripts. Of course, all that's done using Java, and the database itself is actually in Access at this point. So then our hopes, moving forward, we're expanding the fault management database to all the subsystems. So it's going to be observatory-wide in this case. And then we hope to be able to integrate and automate some change impact analysis. As things start to change in the system, we're able to see the impacts of that. And of course, we want to refine the event network and conflict rules. So we're going to have to iterate through and expand to all the subsystems. We're going to have to build a comprehensive set of conflict rules in the process. And then, as stated before, all this is supposed to come up with conflict scenarios that we intend to develop into test cases to execute. And all that said, there's stretch efforts to integrate our portfolio-based risk assessment, risk-based assessments, so that as we go through this process and we identify potential conflicts, there's a possibility that we'll end up generating far more conflict scenarios than we'll have time to actually analyze. So that will help us to prioritize or eliminate certain areas that we'll look at based on our prior risk-based assessment. And then also evidence-based assurance and assurance cases are important. This method is supposed to be deriving some assurance evidence that we've covered scenarios and identified that there are or aren't conflicts in the system. So integrating the goal-structured network GSN to provide a means to generate assurance cases or an assurance structure to this will help to capture and report these out to the project. So then, conclusion-wise, early results of this method have been very fruitful. Be able to find over 300 findings to improve the developers and IV&V's assurance. And overall, the additional effort to this point has been pretty minimal compared to other requirement validation efforts for fault management. There's a little bit of additional effort if you're looking at the FMEA and FTA. Although, as we expand this to other subsystems, there's different developers, different ways of doing the FMEA and FTA analysis, different artifacts. So these numbers may change, but overall, it's been a lot more bang for the buck at this point.
Okay. I did have two, but I think I'll just ask one. You meant got a question. You mentioned early on that software or functionality has been moving towards data-driven data-driven functionality. So like a migration or an evolution from hardware to software into data architectures. I'm curious if your approach is agile enough to continue to assess the dynamic nature of developing those data tables. Is that what the
Yeah,
macros for the change management
that was
is?
really the main driver for this, was trying to develop a method that would allow us to provide assurance and then maintain it as those data structures change. So you see in there, the commands and telemetry are basically data structures. There's so a lot of the software behavior that isn't fault management related is driven by data structures that are configurable, and the fault responses are configurable as well. And so there's a lot of data items in this system specifically that will change and are changing uh, faster than IV&V can do analysis on them at this point.
Right. Time for a Apple. So the second question I had was, and it's a quick one, I think. When you relate two entities, do you only state that one affects the other, or do you explicitly define how the second entity is affected given the inputs? Does that question make sense?
How they're impacted.
Like if item A goes from enabled to disabled, you know that item B changes from on to off, or do you just say when state changes of A, B may change? Are you explicit with how it's affected?
No, it's explicit how it's affected.
So when you have these layers, the local response versus the global response, can you inherit those, or are you really talking about an exponential number of combinations you have to manage?
No, you would inherit those. So this is not a tree. The you're talking about the event network,
Yes.
the system model. It's not a tree. It's a true network where um, it's not uh, it's not two-dimensional. It's three-dimensional, where you have many things mapping back to one another in some spider web, where you can have recursion occurring very easily when you start looking at how the events are related to one another. One event could spark 10 events, which then wrap back around and spark the initial event. So that's something that again, the analysis is supposed to see whether or not there is recursion possible and whether or not that is expected or can